Good morning, everybody. Today, we're going to keep continuing our discussion of compressible flow. I'm going to start with a recap of what we've talked so far about in Chapter 6, then hopefully work a couple problems for at least isentropic flow and adiabatic frictional flow, and depending on our time, possibly get into isothermal frictional flow. So, when talking about compressible flow, we can say that based on the continuity equation, excuse me, that for a system at steady state, with the mass n equaling the mass out, in lieu of our typical analysis of rho 1 u1 a1 equal rho out u out a out, we typically consider things in terms of a mass flux. Because for compressible flow, the mass flux remains constant. And so even though our density and velocity is changing, the mass flux remains constant. And so we can modify our existing equations to, instead of looking at these two variables separately, we can analyze our system in terms of this mass flux. Also keeping in mind that for Reynolds number now, we consider it as G d over mu, which will come into play when considering the mass flux of our system, or essentially finding the friction factors that when we get to there. We also considered that we have to take note of the relative velocity of our fluid. Which means we have to consider our Mach number, where the Mach number is a ratio of the fluid's velocity relative to its speed of sound, which for any given fluid can be denoted by one of two expressions, gamma p over rho, or the square root of gamma t r over the molecular weight, which combining these two expressions tells us that we can solve for a Mach number as the square root of rho u squared over gamma times pressure, or the square root of velocity squared times molecular weight times gamma t r. And we also considered that when our Mach number is equal to 1, we have what's known as the asterisk condition of the fluid, with our fluid properties being denoted by an asterisk. Your velocity wouldn't really come into play because it's not a property. And so the big thing to note is, as we said, we have to think of things in terms of mass flux when looking at our mass balances, and to identify whether we need to consider the more complex compressible flow expressions, we have to identify the fluid's Mach number. If the Mach number is low, and that's relative, typically, usually if it's below maybe see, I don't want to give you a number because it really varies. Maybe 0.1 is safe. You can consider it incompressible. I would say assumptions is reasonable. But if the Mach number goes above this, then you have to consider the compressible flow expressions. All right, and last time we also talked about isentropic nozzles or isentropic compressible flow. Or I would call this flow through nozzles. Where we considered a system that had this type of setup, where we had a reservoir, one pressure, a receiver at another. Then we had a converging section, diverging section, and the throat. And that we can consider things in terms of a pressure ratio. Or if this is P naught and a receiver is P, the pressure ratio is simply P over P naught. Where we consider flow when our pressure ratio is less than 1, where we can have a maximum flow rate, which occurs when we experience choked flow. And depending on the proper pressure ratio, you can have one of several categories of flow in the system. You can have subsonic flow, then subsonic flow, with sonic flow at the throat, you can have sonic/supersonic flow, in the diverging section. And this can be both unstable and stable. And this is kind of part of your synthesis assignment, getting a bigger grasp on this. So I would say see figure 6.2 and synthesis assignment 5. And it's such a, if I could spell right.
What page is that on again?
That's a good question, page 140 in the 7th edition. Yeah, I would probably definitely take a really good read of page 140, 141, and look at figures 6.2 and 6.3. They lay out what you need for synthesis assignment 5, in addition to the link that I sent you, which gives you that MATLAB program to run, which is kind of cool because it's essentially allows you to, almost helps you to design and tune a nozzle for supersonic flow. And I figured that's the best way for you guys to get a solid grasp of isentropic compressible flow, is to kind of play around with things like that and do some more reading. Also, I don't think I explained to you guys, but just so everybody's on the same page, I assume most, if not all of you, can understand the difference between sonic, subsonic, and supersonic flow. But just so everybody's on the same page. Subsonic is when the Mach number is less than 1. Sonic flow is when the Mach number is 1. And supersonic flow is when the Mach number is greater than 1. Now, for my fun trivia time, there is a newer moniker that's thrown about over the past, I don't know, decade or two, for flow with a Mach number greater than 3. Does anybody know what this is commonly referred to?
Hypersonic.
That's correct. Hypersonic flow. The fluid mechanics and dynamics that exist in hypersonic flow are so much more complex to supersonic that then, aerospace experts, physicists, NASA, and even the military are, using this moniker hypersonic flow to consider the implications of systems traveling at these speeds. You can imagine, I'm sure, in terms of space exploration, as well as the development of high-performing stealth and jets and things, that hypersonic flow is of extreme interest to these groups. And if you want to learn more, I would probably recommend you talk to Dr. Murray, as he is our expert on aerodynamic flows and things. But he actually has a supersonic wind tunnel that they've designed that follows this isentropic principle, where he has a window essentially that occurs right at the throat for transport mechanisms, or for essentially observation and data analysis. So he does a lot of things involving high velocity flows. It's really cool stuff. So that was a quick run through of everything we talked about. On Monday, I know it took actually a little bit more time than I expected, but I felt like it was important to kind of reemphasize some of these materials and concepts, as they're not intuitive by any means. Were there any questions or thoughts or questions that you guys may have had now that you've had a night or two to think and sleep on it that I can hopefully answer, we can discuss as a class?
Is choked flow a good thing? Is that what you're going for because it's the maximum flow rate? Because choke just kind of connotates a bad thing to me.
That's a good question. Choke flow is definitely not a good thing. It's essentially a limiting issue where you essentially not in control in terms of manipulation of the flow rate. If you're trying to get a greater mass flow, you simply won't be able to because of the limits of the process conditions. And so choke flow is an issue and not a good thing by any means. Good question. Good question. All right, so let's dive into an example looking at isentropic flow. But before we do, a couple expressions that we have to describe isentropic flow. So isentropic flow equations. The first thing we consider is what's known as a critical pressure ratio. And so the critical pressure ratio, which, let me see what the book uses for the R sub C. It's essentially the pressure ratio when the receiver exists at the asterisk condition. And we can solve for it as P star over P naught, which we can substitute based off some expressions for compressible flow as 2 divided by gamma minus 1 to the quantity 1 minus 1. Oh, sorry. 1 over 1 minus 1 over gamma. And this is equation 629 in your text, page 142. Yeah, unfortunately, reality is all the compressible expression equations are a little messy. So I will give you their locations in the text that you can review. That'd be a little neater than my handwriting.
That 1 over 1 minus 1 over gamma, that's a power of that 2 over gamma minus 1 function, correct?
Yes, correct.
Cool,
This is a power function. So it's basically 2 over 1 minus gamma to the power of 1 divided by 1 minus 1 over gamma.
Thank you.
Of course. The next expression that we'll look at is determination of a Mach number for isentropic flow. We get the Mach number squared is equal to 2 divided by gamma minus 1 times the quantity P naught over P to the, and this is pressure, 1 minus 1 over gamma power minus 1. This is equation 627 on that same page, 142. And then final expression rearranging to solve for P over P naught. We have 1 divided by 1 plus gamma minus 1 over 2 times the Mach number squared. And then all of this on the denominator is raised to the 1 minus 1 over gamma power. Oh, excuse me, it's unfortunately more annoying than that. It's the 1 over 1 minus 1 over gamma power, being equation 628 on page 142. Don't worry, I'll work with an example with you on using some of these expressions, as well as one more expression I think I may have left off, equation 626, solving for velocity in isentropic flow. We have 2 times gamma over P naught over gamma minus 1 times P naught, excuse me, rho naught it's 1 minus P over P naught times 1 minus 1 over gamma, being equation 626 on page 142. All right, so let's look at an example carefully together. So we have air entering a convergent divergent nozzle, basically an isentropic nozzle, at 550 Kelvin with a pressure of 20 atmosphere. If the throat area is 1/2 that of the divergent section, and assuming the Mach number in the throat is 0.8, what are the values of the following quantities at the throat? Pressure, temperature, velocity, density, and mass velocity, g. So I'll give you guys a second to write these things down. Then we'll work together to solve this out. All right. So example 1, we know our pressure in is 20 atmospheres, our temperature in 555 Kelvin, the Mach number at the throat is 0.8, and the area of the throat over the area of the diverging section is 1/2. And so what we're looking for is the pressure of the throat, temperature, velocity, density, and mass velocity. Well, we know that the mass velocity of the throat is simply the density of the throat times the velocity of the throat. So I'd probably grab those two before I grabbed their mass velocity. So the first thing we can look at solving for is the pressure of the throat using equation 628 on page 142. We know that pressure over P naught is equal to 1 over 1 plus gamma minus 1 over 2 times the Mach number squared times 1 over 1 minus 1 over gamma. And so for air,
Is there supposed to be a closing bracket after Mach squared?
yes, thank you. So keeping in mind for air, the gamma is equal to 1.4. And you can, I think Engineering Toolbox has a table of the ratio of the heat capacities for a bunch of different fluids. So we're looking for this pressure of the throat over our P naught. We have 1 divided by 1 plus 1.4 minus 1, which is 0.4, divided by 2, times the Mach number of the throat squared, which is 0.8 squared, all over to the 1 divided by 1 minus 1 over 1.4. If we do this calculation, we should find that this right-hand side is equal to 0.656, which means the pressure of the throat is equal to 0.656, our incoming pressure of 20 atmospheres, which is equal to 13.1 atmospheres. All right, the next thing we can solve for without too much difficulty is the density of the throat. Assuming it can behave as an ideal gas, we can say we can't use that. We would have to find the density or the temperature first, but we can solve for the density at the inlet, knowing that we have 20 atmospheres coming in. Molecular weight of air is 29. The R we would probably use 0.08205. And temperature 555 Kelvin. We do this and we get a density initially of 12.7 kilograms per cubic meter. So we needed this. To solve for the velocity of the throat. Which we can solve using an expression that looks like this. 2 times gamma times r T naught divided by the molecular weight times gamma minus 1 times the quantity 1 minus pressure of the throat over the initial pressure times 1 minus 1 over gamma. And this is essentially combining our Mach expression 627 with equation with our density expression to solve for our velocity of the throat. So if we do this, we get an equation, and here I'll make it big so you can kind of see the steps. 2 times 1.4 times 0.08205. This would be liter atmospheres per mole Kelvin. The temperature would be 555 Kelvin. The molecular weight would be 29 kilograms per kilomole. I would need to convert this to moles. And I can go slower if I'm going a little too fast. Just feel free to let me know.
If you could slow down just a little bit, that'd be awesome.
Okay. And then this is going to be times 1.4 minus 1 or 0.4. I can do a quick unit check.
So, Dr. Lopez.
Yes.
So when you were combining the Mach expression like 6.27 to find your velocity, but since you found the initial density, couldn't you just have used the equation 6.26 to find your velocity of the throat? Or did you have to combine it with the Mach expression 6.27 with the density?
Did I say 6.26? It's 6.26. Sorry, this is the U squared expression. I have no idea why. It's the U squared expression. I just took the square root of it and plugged in
R T naught over molecular weight for P naught over rho naught?
Yeah. Which technically I didn't really need to do.
That's what I was wondering, because you could do it if you did it substituting the R T naught and molecular weight, you'd get the same thing, wouldn't you? Or no?
Yeah, we should be able to.
Okay.
No, we can try it like that. That seems a little more straightforward than what I'm doing. Let's see. I'm willing to go off the cuff. So let's see. 626 says what? We have P naught here and rho naught here. Everything else seems to be the same. Let's see what that would give us. So we have 2 times 1.4. P naught is 20 atmospheres. Rho naught we just solved for, 12.7 kilograms per cubic meter. And then this would be 0.4 because it's gamma minus 1. And then we have 1 minus the pressure of the throat over P naught, which would be 13.1 atmospheres over 20 atmospheres times, or to the power of 1 minus 1 over 1.4. And then this is all square rooted. And then we get some really strange units. Let's see what this gives us as a final solution. Feel free to do the calculation yourself and check with me. So we get So I'm getting a square root of 11.02 times, let's see if I can do this next step. Zero 0.886. So what did you all get on this one?
Did you do 1 minus that 0.886?
Oh, I did not. Thank you. 1 minus 0.886. I got about 1.12. And this is going to give me units of something that's really ugly. I'm seeing cubic meters, atmospheres per kilogram to the 1/2. So there is a way to convert out of this. And I can say 1 atmosphere is equal to 1.01325 newtons per meter squared to the 1/2. And 1 newton is equal to 1 kilogram per meter second squared. So if I do this, the atmosphere to the 1/2 goes away. I end up with the kilogram squared to the 1/2 is just a kilogram. The newton goes away. And so the second Actually, the kilograms are, no, they cancel each other out. Because I have a kilogram to the 1/2 on the bottom and a kilogram to the 1/2 on the top. And I should be, I have a second, because I have a second squared to the 1/2. And it looks like I have what? With my meter squared. Do those cancel? I should be left with a meters on top.
Lopez, that could be 101,000 pascals in an atmosphere.
Oh, I never gave you the scientific thing, sorry. Let me rewrite it, 1.01325 times 10 to the 5th. Thank you. Thank you, thank you. No, that would be why. All right. This is why you always be really careful with your notes. So this gives me meters to the 4th on top, meters squared on the bottom, which gives me just meters to the 1/2, which is meters. So if I do this, I should end up with approximately 355 meters per second for my velocity. So let me clean this up. Turns out we didn't need to do the convoluted. We can just use 626 directly. We end up with some ugly units, but with some careful unit conversions, we can get approximately 355 meters per second, which is about 1,167 feet per second. Did everyone follow that okay? Or do I need to go back and re-explain it?
That made sense.
Okay. So now we have the velocity of the throat. To find the density of the throat, we can use equation 623, which lets us create this expression, the density initially times the pressure of the throat over the initial pressure to 1 over the gamma. This is equation 623 on page 142. So with this, I can say my density, which was, I think, 112.7 kilograms per cubic meter times my 13.1 atmospheres over 20 atmospheres, divided by 1 over 1.4. I do this and I should get a smaller density of 9.41 kilograms per cubic meter. Now that I have my density and my velocity, I can solve for my mass flux or my mass velocity at the throat, which is just the 355 meters per second times my 9.41 kilograms per cubic meter. And I'm left with approximately 3,340 kilograms per meter squared second. And then the last thing I can obtain is my temperature at the throat. Which is going to follow this expression.
Dr. Lopez, could you zoom out just a little bit?
Sure. How's that? Is that better?
Yes, thank you.
Of course, happy to. And so the pressure of the throat is 555 Kelvin times 13.1 atmospheres over 20 atmospheres times the quantity 1 minus 1 over 1.4. Which gives us approximately 493 Kelvin for the temperature at the throat. All right, so basically using the expressions on page 142, we're able to identify the fluid conditions at the throat based off of the given variables. And if we wanted to, we won't do it in this class, but if you want to take a deeper look, it's on page 144 and 145. There's a follow-up to this problem, which identifies the fluid properties at the asterisk condition based off of what's identified at the entrance and at the throat. But any questions on this example? If not, let's consider briefly an analysis of adiabatic frictional flow. And so what do I consider when I'm considering adiabatic frictional flow? If I say something is adiabatic, what can we assume?
There's no heat transfer.
Yeah, so there's no heat transfer, or my Q dot equals 0, and I have what's known as an insulated pipe, where I have no heat transfer, or that it's small enough that I can consider it negligible. However, I still have friction in my system. And when considering compressible flow, my friction parameter in compressible flow exists as a function like known as this, where we have our friction factor times our flow length divided by our hydraulic radius. And in lieu of doing a lot of very large derivations, one thing we often consider is for compressible fluid transport, we consider an average friction factor, F bar, which is equal to the friction at the inlet plus the friction at the factor at the outlet over 2. Because since the fluid velocity is changing, the density is changing, in actuality, the friction factor is changing as well. However, it's a lot easier to obtain reasonable approximations for our frictional dissipation if we consider an average value and base our calculations off of this average. One thing that we often consider as a rule of thumb is that for supersonic flow, we often find that the friction factors that we obtain are a fraction or about half of what we see in subsonic flow. And so when going from considering frictional dissipation from, we'll say, point A to B in adiabatic frictional flow, we have the following equation, which we see as equation essentially 638 on page 147, which states that our friction expression, F bar times L over our hydraulic radius, is equal to 1 divided by gamma times the quantity 1 over the Mach number at our point A squared minus 1 over the Mach number at point B squared minus gamma plus 1 over 2 times the natural log of our Mach number at point B squared times the quantity 1 plus gamma minus 1 over 2 times our Mach number at A squared, all divided by our Mach number at A squared times the quantity 1 plus gamma minus 1 over 2 times the Mach number at B squared. And this is all within the natural log. And so one thing that we can consider is we can result in choked flow are essentially Mach number at point B that we're considering is equal to 1, which means that tells us, depending on for a given fluid length or pipe length, traveling from point A to point B, we can identify when we'll obtain choked flow when we set our second Mach number equal to 1. And so this tells us what our max conduit length is for adiabatic frictional flow. And so we can rewrite equation 638 like this: 1 over Mach num A squared minus 1 divided by gamma is minus 1, excuse me, plus 1 over 2 times the quantity of ln of 2 times 1 plus 1 minus gamma minus 1 over 2 times our Mach number A squared divided by our Mach number at A squared times gamma plus 1. And this expression is equation 645 on page 148. All right, so I think that's all we have time for today. We'll pick up here on Friday, finishing our discussions in adiabatic frictional flow. We'll work an example. Then we'll talk about isothermal frictional flow and work another example. Any last minute questions?
Yeah, for when you're giving the isentropic flow equations for the critical pressure ratio, and the pressure is an asterisk condition, does that mean you can only get your critical pressure ratio if it's sonic flow? Since the asterisk condition would be when the Mach number is 1?
Yes.
Okay.
Any other questions?
What day did you say our test was? Was it next Tuesday, right?
Your test will be next Tuesday, yes. And I'll hold a review section next Monday.
What time will it be on Tuesday? Would it be the same time as
It'll be from 6 to 9 p.m.
Okay.
I believe so. It's on the syllabus and on the schedule.
Is the compressible flow material going to be on the test?
The compressible flow will not be on the test. It'll be over modules 1 through 4.
Okay.
Good question.
If we were wanting to use one of our late homework submissions, Dr. Lopez, when do you want those to be turned in?
That's a very good question. I typically release solutions probably the weekend before a midterm. So I'll probably release homeworks solutions Friday or Saturday. So I probably want them in by Friday.
Okay, sounds good. Thank you.
I'll send a follow-up here shortly. Thank you for that reminder,
Yes,
Walker.
Will we be on Zoom during the exam, or how will it take place?
I'm not going to require you to be on Zoom. The way it's going to take place is the exam will be released in Blackboard at 6 p.m. and you'll have to submit it into the same window, essentially like an assignment, by 9 p.m. I will be on Zoom to answer questions.
Okay.
Via the chat feature. But to be honest, I don't see any other way beyond the honor system, because I don't want to have to police something that is occurring virtually. And so you guys have enough stress. I have enough stress and work as well as you. So we'll just go from there. All right, guys, take care. Have a great day.
Dr. Lopez?
Yes.
When did you say you were going to hold that review session again? I missed that.
It's Monday evening. I typically do it from 5 to 7. I believe I had it on the schedule.
Okay, thank you.
I'll send a reminder about all of this here probably later today.
Awesome. Thank you
No
so
problem.
much.
You're welcome. Take care.
Thank you. Bye.